Hi guys, this is our second to last video. We're still doing electrochemistry, which is chapter 19. I did want to let you know I went ahead and posted a standard reduction table, which we're going to go over how to use those in this video. So it's in week 4. All right. So electrochemistry is the study of those redox reactions. And we're mostly going to be talking about electrochemical cells, specifically voltaic, which is the spontaneous one. Okay, I do need you to understand the word voltaic and galvanic both mean spontaneous. And again, those are the ones that we're going to be focusing on. The non-spontaneous ones are called electrolytic cells, but because we have to give them energy, we're not going to focus on those. Only the voltaic or galvanic are the ones that we're going to focus on. We will go through one electrolytic, but that's it. All right, so just remember a spontaneous reaction is one that happens on its own. In this example, we're zinc and copper. So the copper solution is going to be plated onto that zinc metal, and the zinc's going to come off. All right, so we're going to have electrical current, and that's how we're going to measure the spontaneity of that reaction. Just remember that delta G is negative for spontaneous reactions. And again, that those voltaic or galvanic cells, those are the ones that we're focusing on that are going to be spontaneous. So we are going to be focusing on those half cells. And for a circuit to happen, the electrons have to flow through a wire, and the ions are going to flow through a solution in a salt bridge, and we'll go over all of this when we see the picture in a minute. And the electrodes are going to be solid. And for the lab y'all are doing, y'all got the pieces of metal in your lab kits, and then you've got the LED, and you've got the wire. All right, so the anode is where oxidation occurs. And there's the way to remember that is anox. And then the cathode is where reduction occurs. This is red cat. That is a horrible, there we go, red cat. Okay, so anox and red cat, that's how it's easy to remember. The anions are going to be attracted to the anode, and those cations will be attracted to the cathode. And then the anode is connected to that positive end, but that's in an electrolytic cell, so we're going to wait on that. So for the voltaic cell, again, we've got the anode and the cathode. There must be a wire connecting them. The electrons will always flow from anode to cathode. Okay, from anode to cathode, that's always the way they flow. And the salt bridge in the middle, okay, the ions flow to the direction that the charge is changing. So this positive cation is flowing towards where the electrons are going, and the anion is flowing to where the electrons are leaving from. And the flow of electrons is fat cat from anode to cathode. I know it's not great, but fat cat is from anode to cathode. All right, so voltage, that's what we use to measure. That's the difference in that potential energy, and our unit is going to be volts. Later, we're going to talk about the electromotive force, and where currents come in amps, but not yet. All right, for cell potential, that's what we call it when we're measuring that voltage. That's the difference in potential energy between anodes and cathodes. And just remember, reduction happens at the cathode, oxidation happens at the anode. And E cell, that's for the whole reaction, is what the E cell is. And just remember that the little degree sign means standard conditions. So we're looking at 25 Celsius, 1 atmosphere, 1 molar. Okay, here we see some cell notations, and there's going to be different ones. The electrodes, or the solid ones, will always be on the outside. The aqueous ones will be on the inside. And this double line bridge just indicates that we're changing sides, so that's where the salt bridge is. So here it's showing you at the bottom, we've got that cell notation, and where the anode is oxidized, and again, the cathode is reduced. And just, you're not going to have to write them like this, but you are going to need to be able to go from the cell notation and understand what's happening. So the anode is, again, oxidized, that cathode is reduction. And just so you know, there are electrodes that are inert, and that just doesn't participate in the reaction. All right, so here's a bigger one with an inert cell. That platinum electrode is inert, and so notice there's more happening here, and that's just because there's more in our aqueous solution. You need to put everything that's aqueous in that aqueous section. Okay. Then standard reduction potentials, we always compare it to the hydrogen electrode, and that's because it has 0 voltage to start out with. So you'll see on the table that I posted, the standard reduction table, we're going to compare everything to that standard hydrogen electrode. All right, and for half cells, our half reactions with stronger tendency towards reduction will have a positive value on that chart. Standard tendency towards oxidation will have a negative value on the chart. And here's our flow of electrons. They always flow from anode to cathode, that fat cat. Okay, from anode to cathode. Again, you just have to remember that. And we're going to see in a minute, but we're going to want our E cell to be positive for the spontaneous reaction, so that voltaic cell. Okay. So the higher on the table that's in week 4, the stronger the tendency it is to be reduced, and the lower, the stronger the tendency it is to be oxidized. And just so y'all know, the entire table is a reduction table. So all the ones for oxidation, you're going to have to flip them because they're not being oxidized, they're being reduced. So here's a table. You can see those ones at the top, those are positive values. At the bottom, they're negative values. And again, the ones on the bottom are going to want to flip to be that positive value. Also, when we multiply these half reactions, we do not multiply the values, the voltages. Even though we did that in chapter 18, we do not do that in chapter 19, okay? And actually, I don't even like this equation down here. I like E cell is equal to, okay, and the way we're doing this positive is because when we flip that oxidation, it's going to change the sign for us. In the bottom one, they're not flipping it, but we're going to go ahead and flip them because it's easier to remember. You're not getting messed up with negatives, anything like that. All right, so here is a reaction, and we need to find its cell potential. Okay, so we pull out the half reactions, which we've been doing. Notice there's 3 electrons on each side. And then these values come from that cell potential table. But the one that's oxidized would have been it should have been flipped. Maybe these are the flipped values. Because I don't have the table up, let me see if there it is. Okay, so that aluminum was negative 1.66, but notice here the electrons are on the reactants, but here they're on the product. So I would have preferred y'all to do this, say plus, and then just add them. Okay, so that 2.62 volts. All right, so here's another one. We've got lead and chromium. So we go back to our chart. It was Pb2 plus and Cr3 plus. I just want to double check. Yes. Okay, so our lead is 0.13, and that's negative. And our chromium is 0.73, negative. Okay, so when you're faced with this, even if you don't have a reaction in front of you, which we do, we want it to be voltaic. So we're going to go ahead and flip the more negative one because we want that one, the whole thing, to be positive. And so if we do that, I've got 0.73 volts plus negative 0.13 volts, and I've got 0.60 volts. Okay, really this is not that hard. Also, if you see here, the lead is being reduced because it's from +2 to 0. And the chromium is the one being oxidized, so that's the one that has to flip. Just match it to the equation on the chart, and if it's not that, then go ahead and flip it, which means you change the charge. All right, so spontaneity, again, positive ones that have positive value will be spontaneous. If they have a negative value, they will not be spontaneous. So here it wants us to predict if it's spontaneous or not, but first you need to look at the chart. So here's our chart. We had what? Iron and magnesium. Okay, iron is being oxidized. I don't think. Okay, so once it's been oxidized, you've got to change the sign. So then this, you add them together to check. So this is negative 2.37 and then 0.45. I didn't grab my calculator, so I've got 2. Okay, so negative 1.92 volts, so that would not be spontaneous. I guess it doesn't give you the answer. Okay, but it's not spontaneous. And if we were to do iron and lead, and it's the same iron, so it would be positive 0.45. The lead would be negative 0.13, so it'd be negative 0.13 and 0.45. I get 0.32 volts. That is positive, so B would be spontaneous. Okay, it did want you to sketch the cell to just make sure you know the flow of electrons. You know, the anode, when you draw them, is normally on the left and the cathode is normally on the right. You will see that on the homework, and it can be the other way. This is the conventional way that the anode is on the left and the cathode is on the right. All right, so predicting whether metals will dissolve, you have to use an reactivity chart. But if the reduction of hydrogen is easier than the reduction of the metal, then it will dissolve. Okay, and most metals dissolve in acid. And the way to tell, if you look on the chart, hydrogen is here at 0. So you just need to know, will it dissolve? Okay. And which means if the reduction of hydrogen is easier than the reduction of the metal, so hydrogen just needs to be higher than it. And again, if we go back to the chart and look, a lot of metals are below that. So you can tell that way. There may be one question like that on the homework, but there's not any on the test. All right, and then that's where we're stopping for the day. Y'all have a good day.